Okay, thank you. So our next speaker is Eliane Lazzari from University of Liège, and she'll be speaking to us about the pyrolysis wood oil.
Thank you, Kate. So, as already introduced, my name is Eliane Lazzari, and currently I'm working as a postdoc at TotalEnergies in a project that's in collaboration with the University of Liège. So today I plan to talk about the qualitative screening of catalytic pyrolysis with oil by means of GC-TOFMS and soft ionization. However, as we got some good results also using the recycled plastic pyrolysis oil and this approach, I decided to add a first topic on this in my presentation. So, TotalEnergies is hard work in the transition from fossil-based to bio-based fuels. In the recycling, the company aims to produce 30%, let me see where is the point here, 30% of recycled and renewable polymers by 2030. Inside this number, we have the chemical recycling as pyrolysis. So the pyrolysis returns the polymer to its original monomer and can reach the circular economy needs. And my project is here to try to understand the composition of this plastic pyrolysis oil by the GC. So here we have a 2D color plot for a plastic pyrolysis oil using the reverse phase and GC FAD flow modulator system. So we can see in the bottom the aromatic compounds, in the top the posh, the paraffins, the olefins, and the de-olefins. Here is very important because the olefins are well separated from diolefins. And for us, the diolefins can cause some troubles in the unit. So we needed to remove them by upgrading process. Even by GC, we have a good group type analysis, so you can understand where is the within each class. Sometimes we need to go for the identification of these peaks and then go for mass spectrometry analysis. In the inclination of the GC with MS, as we know, the electronic impact X, the electrovolts, is the conventional ionization source used. So this is a hard ionization, so we're going to have a spectra with many fragments that can be compared with a library. However, once using the hard ionization, the assignment of ion compounds is sometimes challenging because the paraffins and the isoparaffins and the olefins and naphthalene display similar spectra at 70 electrovolts, and also the parent ion, the molecular ion, is not preserved. So this can cause some doubts in the assignment of the compounds and also in the evaluation of the upgrading process, as I'm going to show in this example. So here we have a zoom between C10 and C11 in the left side of a feed and the right side of a effluent. Effluent is after upgrading process, after hydrotreatment. If you go for the highlighted regions, we can see that the diolefins have almost disappeared in the effluent, so this was the goal, and the olefins were decreased, but the amount of olefins is still present in the effluent was higher than what we were expecting for. So we keep in mind, are these peaks still olefins or are another compounds? And then we went for the analysis using the PI. So the PI, the GC PI, is a soft ionization, so going to give us a spectra with limited or no fragmentation and retain the molecular ion. So as you can see in the first spectra, we have a PI for any paraffins, so we have the molecular ion, and in the bottom we have the PI for isoparaffins. We have also the molecular ion, and here I just want to highlight because the PI can give us some fragmentation partners that can help to understand the structure of the compounds that we are talking about. But for us, the most important useful information get by PI was the distinction between olefins and naphthenes. So here we have the spectrum of alpha olefin, where we have the molecular ion and some fragments. And once we go for the naphthenes, we have the molecular ion, but the fragments coming from the ring. So once we have cyclohexanes, I'm sorry, we're going to have the fragment 68, cyclohexanes 82, and cyclohexanes with methyl 96, and so on. So once we're going back to our example, and now we're going to analyze this sample by GC-TOFMS, what we can see that the peaks before we thought were olefins are indeed naphthenes, because these spectra, they show us the fragments coming from the ring, like here. We have the fragment 82, 96, and so on. So I'm going to change subjects, just a little bit, and go for the biopyrolysis oil. Once we think about energetic transition, the biofuel produced from lignocellulose biomass by pyrolysis has a big place in the table. And now we started to explore this matrix for the production of sustainable aviation fuel. So in order to reduce the carbon footprint in the aviation market, TotalEnergies aims to produce 1.5 million tons of SAF per year by 2030. However, to reach this goal, we have some challenges to overcome. The first of them is the diversification of feedstocks. As a part of the feedstocks already used for SAF, as used cooked oil and animal fat, we have the lignocellulose biomass that started to be explored. However, contrary to the fossil-based fuel, the lignocellulose biomass, the composition, presents a lot of oxygenated compounds, since it is composed by cellulose, hemicellulose, and lignin. Once those polymers are broken down by pyrolysis, we're going to have the liquid product that is called bio-oil, but still we're going to have a lot of oxygenated compounds in this biofuel. And this causes instability to the biofuel, corrosion properties, and once we think in a petrochemical world, can cause catalytic inactivation. So to improve the quality of this biofuel, we need to go for a migrated process. As example, the hydrodesoxygenation. So the hydrodesoxygenation is a process that uses temperature, pressure, hydrogen, and catalyzer to remove the oxygen from the compounds and to increase the amount of hydrocarbons as aromatics, naphthenes, paraffins, and isoparaffins. So the composition is going to depend also the conditions that we are using in the hydroxygenation. However, to check the quality of our biofuel and also if the hydroxygenation were able to remove all the oxygenated compounds, we need to have a well-designed analytical approach. So going for the samples and the method that we used. In the left side, we have the samples. So in this project, we analyzed HDU wood pyrolysis oil, 6 effluents. The difference among the effluents was the timing that these samples were present with the catalyzer. Being the effluent 6, the higher time. So here I'm going to speak about effluent 1 and effluent 6. So in the right side, we have the conditions used for the method in the EI and PI mode and the normal phase setup. So this figure is show us the 2D color plot for a normal phase separation of the effluent 1. what we can see initially, that is a complex sample, but the peaks are well separated for the conventional setup. So we have the illusion of any paraffins and isoparaffins in the bottom, and in the top, the polyaromatics. But we don't have anymore the good group type analysis as in the plastic pyrolysis oil. So to try to identify what is inside of this sample, we use some tools. The first one was the extraction ion chromatogram. So in this table, we have the chemical classes that we can find in the biopyrolysis oil, the common ions in the EI ionization, and now some compounds examples. So let's focus in the naphthalene and phenols. So here I am comparing the EIC, the chromatogram, for the naphthalene 1 ring and naphthalene 1 ring with the unsaturated carbon chain. So the first one, we extract the ions that are described above, and the second one, the ions described below. So in the top, we have an example of the EI chromatogram for these chemical classes. So these chemical classes can be composed by cyclopentanes or cyclohexanes, but we cannot distinguish them just using the EI. So we went also for the PI analysis. In the PI, you can see for the naphthalene 1 ring that the spectra show us the ion 96, and we didn't find the ion 68. So probably we are talking about cyclohexanes and not cyclopentanes. Moreover, by PI, we confirmed the molecular ion, and we were able to group in congeners. So the peaks that are under the dot red line are all then have the same molecular ion. The same profile of PI was found for the naphthalene 1 ring with unsaturated carbon chain. So we can see the molecular ion confirmed, and also the fragments coming from the ring. So just to highlight, these compounds are eluting as expected, just above the naphthalene 1 ring. And go through the phenols. So for the phenols, we extract the I-107. So we can see the illusion of the alkyl phenols. Starting in C1, that means a methyl linked to the phenol, until C7. So in the right side, we have the examples of the EI spectra for these phenols. The PI of phenols show us a spectra dominated by the molecular ion, as we can see, for example, the phenol C2. But we also got some small fragments that can give us an insight about the structure of the phenol that we are talking about, especially once we want to differentiate isomers. So if you go for the first spectrum, we can see that we have the loss of 29. So maybe we have here ethyl phenol, and in the second spectrum, we have the loss of 15. So here we are talking about dimethyl phenol. But as I already spoke, the phenols are considered contaminants in this sample because they are oxygenated compounds. So if you want to go, and they are within the same region than the monoaromatics, as we can see here. So if you want to go for quantitative analysis or better understanding of the oxygenated compounds, will be complicated just using the normal phase approach. Because of this, we went for the reverse phase approach. Here we have the example of the chromatogram of A21 for the reverse phase approach. So we have the paraffins eluting the top, the naphthenes well separated, and the aromatics and polyaromatics are gathered, especially in the ending of the chromatogram. However, we were targeting oxygenated compounds. And once we give a zoom, we can see now that the phenols and other oxygenated compounds are eluting in the bottom. So it was easy to identify that once compared to the normal phase approach. So comparing samples, the effluent 1 with the effluent 6. Here we have the normal phase setup for the total ion chromatogram. So what we can see at the first view is that the effluent 6, we have less naphthalene compounds because they are in this region, and a high amount of polyaromatics because they are in this region. For the phenols, if we extract the ION107, we're going to have that we have more phenols amount in the effluent 6 than effluent 1. And this is also confirmed once we use the reverse phase approach. So here we compare the two samples in the reverse phase. We can see initially that the naphthenes in the effluent 6, they are in less concentration. And also we have more oxygenated related compounds. We found some that we didn't find in the first effluent. This is for the first region of the sample. In the second region, you were able also to see some oxygenated compounds that we didn't find in the first effluent. So what we can conclude about this is that after a time, the catalyzer lost the power to convert the oxygenated compounds, to remove the oxygen from the sample, and also to convert aromatics or polyaromatics in naphthenes. So I would just to finish, I would like to highlight another sample that we analyzed using the same reverse phase approach. And here we can see that the paraffins are emitting in the top. We have a good separation of the naphthenes, the monoaromatics, and the polyaromatics. And also we can see that now it's easy to see that the phenols are not present in this sample because they should be in the region, the highlighted region. To better separate the polyaromatics in this sample, we went also for the normal phase setup. It's just to merge both setups. So here we have the better evolution of the polyaromatics, starting in the monoaromatic, diaromatic, and triaromatic. So is this that I'd like to present today? Thank you for the committee for being able to present here, and all the team from TotalEnergies and the University of Liège. Thank you for your attention.